Hi, AP Stats. Today we are talking about density curves and then the most famous density curve, which is the normal distribution, and how the empirical rule applies to that. So a density curve is an idealized picture of a set of data. Its characteristics is that it's on or above the x-axis, and the area under the curve adds up to 100% or 1.0. The idea behind a density curve is that we can find what percentage of the data falls between given values. So for instance, looking at the picture here, if I wanted to know what percent of the data was between a 1 and a 2, I would just need to find the area of that red region, which we would do by length times width because this graph is a rectangle. Okay. So you can see that red area makes up about 1/4 of the picture, the blue line. So that would be 25% of the data would be between 1 and 0 or 1 and 2. So that's the beauty of a density curve, is that we can figure out what percent of the data is in different parts of it. So, for instance, moving down here, it says, what is the total area of the density curve above? Well, obviously it's 100%. It's a length times width thing. The width is 0.25, the length is 4. 4 times 0.25 is 1, or 100%, okay? Then what percent of the area under the density curve where x is more than 4? Well, more than 4 would be over here. Okay, and again, that's going to be 0.25 because the width is 0.25 and the length is 1, so 1 times 0.25 is 25%. So that's this one. Going to this question, find the percent of the area under the density curve where x is less than 2.5. I'm going to change colors to highlight. 2.5 is here, and that goes down to 1, so it's this area right here. So the length is 1.5 and the width is 0.25. So 1.5 times 0.25 is 0.375. So a density curve just allows us to compute the area, and that turns into a percentage of the data that's in that region. Okay. So you can see this one, find the area of the density curve where x is between 2 and 3.5. I'm going to change colors one more time. 2 is right here. 3.5 is right here. So the width again is 1.5, just like it was with the blue area. And the length is 0.25, so I end up with 0.375 again. Okay? So that is a density curve. We're going to be studying the most famous density curve, which is called the normal distribution. And the normal distribution is just another name for a unimodal symmetric distribution. It is also called a bell-shaped curve. We were introduced to this, to these curves, if you remember back in the Jamboard we did. Right, to match the description of the data to the curve, and one of them was this bell-shaped curve. So if you look to the right, these are all bell-shaped curves. Notice they're not all the same. Some are really tall and narrow, and some are really wide and short. But all of those make the shape of a bell. Okay, so those would be all examples of a normal distribution. You can think of it this way: there is a normal model for every possible combination of mean and standard deviation. Okay, so if you said, hey, I want a model with a mean of 5, standard deviation of 2, I could draw that. Or a mean of 100, standard deviation of 1,000, I could draw that. Any two numbers you could throw in for the mean and standard deviation, and there's a normal distribution that I could draw based on that information. Okay. You'll see this notation in this paragraph right here in the middle. When we write, oops, sorry, didn't let you see that. When we write n, and then parentheses, mu and sigma. Okay, remember mu is the population mean and sigma is the standard deviation. And if the n's capital, that means it's talking about a normal distribution or a normal model with that mean and that standard deviation. Okay, and remember, we know where to draw the mean. If you look over here to the right, the mean is always right in the middle of a bell-shaped curve, right? So we know that is right here. Okay. And then if the standard deviation just tells us how wide to make the graph. Okay, a small standard deviation might look like this one to the right. And a graph with a bigger standard deviation would look like this, okay? Or anywhere in between. So when we see n with 100, 15, it means you have a normal distribution with a mean of 100, a standard deviation of 15. And remember, with a unimodal symmetric distribution like this, the center is the mean, right? And the standard deviation is the spread measurement. So works perfectly in this situation. Now, in statistics, we have what's called the nearly normal condition, which means the shape of the data's distribution is approximately unimodal and symmetric. This condition can be checked with a histogram. So remember, real data is never going to be perfectly symmetric. If you look at these two histograms that are drawn below, they're not perfectly symmetric. Like if they were, this one and this bar would match up, okay? And this bar would match up, but they don't. But real data is never going to be perfect, okay? So one thing to think about is this sentence right here. If you dropped a bed sheet on top of the histogram, if it would basically smooth out to a bell-shaped curve, you can call it approximately normal. Okay, so the idea is, if you look over to the right, here's my histogram, okay? And we're like, well, it's not perfectly symmetric. Well, if I took a big bed sheet, like a double bed sheet, and dropped it on that, okay, so that it would just fall over the top and look like this, then you could forget about the histogram underneath it and look at the overall red shape. If that's looks like this bell-shaped curve or close to it, then it's approximately normal. So you can see on these, I drew in the bell-shaped curve over the histogram. So those two graphs below are very good, like very close to being perfectly normal, okay? Like our data will probably not be that good usually, okay? So it just has to be close. Now, if that's the case, that your data is that bell shape, then the empirical rule kicks in. And the empirical rule has another name. In some textbooks, it's also called the 68, 95, 99.7 rule. Okay, depends on the book you're reading. So the empirical rule gives us a rule of thumb for approximating the proportion of a normal distribution that falls within 1, 2, or 3 standard deviations of its mean. It's also called the 68, 95, 99.7 rule. So keep in mind that this normal distribution is a density curve, which means the area underneath it adds up to 1, okay? So one thing I could show you right off the bat is if I have one of these and I cut it in half with the mean, can you tell me what percent is on this side? Well, 50%. And what percent would be on this side? Well, 50%, because the mean will divide it in half, and it's got to add up to 100% total. So that's kind of the idea here. But this rule is very interesting. If you look at the top up here, it says 68% of a normal distribution can be found within 1 standard deviation of its mean. So basically, if you go 1 standard deviation on either side of the mean, there will be 68% of the data in that region, okay? And if you think about this for a second, that's super interesting. I'm going to back up. Well, I'm not going to back up. Remember the slide before, the first slide of this unit, or second slide, when I showed you normal distributions? Remember, some were really narrow and tall, some were really wide. It does not matter which of those you're looking at. Okay, if it's bell-shaped, then this 68% rule applies to all of them. Okay, if you go out 1 standard deviation on either direction, you get 68% of the data. Okay, second rule, second part, 95% of a normal distribution can be found within 2 standard deviations. So instead of just going 1 standard deviation in both directions, like this is 1, this is 2, and then going 1 back and then another back, that will be 95% of the data. Okay, so 95% of the data is captured by going out 2 standard deviations from the mean. And again, that works in every normal distribution. And then the third part, you can probably guess what this is by now. 99.7% of a normal distribution can be found within 3 standard deviations of its mean. So if you go out 3 standard deviations in both directions, that's 99.7%. So in a true normal distribution, there will not be much data that's above or below 3 standard deviations. Okay. If you remember, we actually said when we studied outliers that anything more than 2 standard deviations away from the mean is a way to find outliers. So by that rule, in this situation, it'd be telling us that, if you look at the graph, that everything in this green area that I'm circling right now, and everything over here, would be considered an outlier if there was data in that area. Okay, that's by that, the 2 standard deviation rule. Okay, so we can use this rule on any normal distribution. So let's go to our example. IQ scores for a certain population are normally distributed with a mean of 100 and a standard deviation of 15. This is actually true. Okay, for people on planet Earth for the last 1,000 years, the IQ has not really changed. Okay, the average IQ is about 100. 68% of people have an IQ between 115 and 85. Okay. 95% of the people have an IQ between 70 and 130, if you're looking at the bottom of the graph. And then 55 is a very low IQ, and 145 is a very high IQ. Anybody above 145 is super smart. And actually, anybody above 130 is considered, would be like an outlier, right? So if your IQ is above 130, you are super smart compared to everybody else, okay? But we can use this empirical rule then to answer questions about this distribution of IQs, which we'll do on the next page. So here's our picture of IQs. One question I could ask you is, what percent of the population has IQs below 100? And that's pretty easy because 100 is the mean. Remember, if I was drawing this distribution, it'd be 115. So we know that's 50% because half the distribution will be to the left of the mean and half will be to the right. So the second question, what percent has IQs above 100? That's 50% also. Okay. So all of this area, this half is 50%, and this half is 50%. Okay. Let me erase those quickly. Now, next question. What percent of the population will have IQs between 85 and 115? Well, here's 85, here's 115. Those are 1 standard deviation above the mean, so going plus 15, and it's 1 standard deviation minus or below the mean because I subtract 15. So that should be 68% of the data. So on planet Earth, if you had 100 people in a room, 68 of the 100 on average would have an IQ between 85 and 115. So almost 7 out of 10 people. Okay. Next question, what percent of the population will have IQs between 100 and 115? Now, this is where you have to use your head a little bit. I'm going to switch colors. Between 100, which is in the middle, if you look at the graph at the top, and 115, which is right here. Well, that's half of the whole distance between 85 and 115. And by symmetry, then I could figure out, well, then it would have to be half of 68. So half of 68 is 34%. So if you're looking on the graph, you'd have 34% here and 34% here. Okay. So that's the kind of game you can play. You can use symmetry to help, right? Let's try this one. What percent of the population will have IQs between 70 and 130? Well, 70's here, 130's here. That's 95%. That's 2 standard deviations in either direction. Okay. Let's shrink this down a little bit. And it says, what percent of the population will have IQs between 70 and 100? Well, 70 to 100 is half of 70 to 130. And we said that 70 to 130 was 95%. So 70 to 100 is half of that, so I would take 95 divided by 2 and get 45%. The next question, what percent of the population will have IQs below 70? So I'm going to draw another picture for this one over here. Okay, so 1 standard deviation is here, 2 is here, 1 is here, 2 is here. This was 100, 115, 130, 85, 70. Okay. So here's what we know. Below 70 would be this little red shaded area. Okay. Now, what I do know is that from 70 to 130 is supposed to be 95% of the data. So if you think about those two red areas that I drew on this picture to the right, how much is in those two little on each side, on each tail? Well, if the middle is 95 and the whole graph adds up to 100, that means there's 5% total in each of these tails. But I only want one tail. I only want the below 70 part. So I'd have to divide that 5 in half, which is what I did here. So 100 minus 95 was 5, but that 5 is on both sides of the graph, and I only want one side. So 5 divided by 2 is 2.5. And then here's another question. What percent of the population will have IQs above 145? Let me draw this one quickly. So here's 100, 115, 130, 145. So 145 is 3 standard deviations away from the mean. Okay? And if we went 3 standard deviations this way, it'd be 85, 70, 55. So we know that in between those two red areas is supposed to be 99.7% of the data from here to here. So what's left over? Well, 100 minus 99.7, which is 0.3. But that 0.3 is divided up equally into these two sides. So I only want what's above 145, which would be this side of the graph that I'm highlighting now. So I'd only want half of the 0.3. So if I took 0.3 divided by 2, that's 0.15%. Okay? So that's 15 hundredths of a percent. Okay? Just to be clear. That's not... okay? So that's the kind of thing I have to be able to do. Good luck with the empirical rule, and we'll see you later.